In this session, we're going to talk a little bit more about what entropy actually is. This is the second screencast in the Thermodynamics unit. You can follow along in your book in section 16.2. Our goal here is to think about the sign of entropy for chemical and physical processes and get a little more intuitive sense. And then start to think about how entropy relates to probability. But there is a separate screencast where we go into more depth about the relationship between entropy and probability. So you can look for that one too. Okay, so last time we said that entropy is the other factor, in addition to enthalpy, that helps us predict the spontaneous direction of a chemical reaction. We said that entropy was something like molecular randomness, related to how dispersed the energy or matter of a system was. And we said that spontaneous reactions move toward greater, more uniform dispersal of matter and energy. So greater, more uniform dispersal of matter and energy is greater entropy. So with that, which phase of matter has the highest entropy? The phase of matter with the highest entropy is a gas. If you look at the pictures, the gas molecules are more dispersed within the container. They're moving faster. They're moving in more different ways. And so that means they're the most dispersed. And so that means that they have the highest entropy. Entropy increases with temperature and also with more degrees of freedom. So we can explain what's going on here. First, for temperature, if you look at the figure on the left, we've talked about a figure like this before, where at the lower temperature, more molecules have the same kinetic energy, whereas at higher temperature, the curve flattens out because more molecules have different kinetic energies. And so because the kinetic energy is more dispersed over different molecules, that means that higher temperature has more entropy. In the same way, we said that entropy increases with degrees of freedom. And so if we think what we mean by degrees of freedom are the way that molecules can move. They can translate, they can move in the X, Y, and Z direction. They can vibrate, which means they can stretch their bonds and compress their bonds. Molecules can also rotate, so they can flip end over end. And if we think about the states of matter and look at these molecular level pictures, we see that solids have very little ability to translate or to rotate while the solid molecules are in their specific spots. The liquid molecules have more freedom to translate, mostly in the condensed phase in the two directions of, sort of on the bottom of the container. They can also rotate a little bit more freely. Whereas gas molecules, they can translate in all three dimensions very freely, and they can rotate and vibrate. And so that means that the gas molecules have more entropy than the solid because they have more degrees of freedom. Okay, we talked about how entropy can increase as temperature increases, but there are some other factors too. Entropy can increase when volume increases, like for a gas. Entropy increases when different kinds of particles are mixed. That could be either gases or solutions or liquids. And entropy increases when the number of independent particles increases. So when we have more moles of gas, if you will, then we see that entropy increases. So thinking about those things, for which of these processes or reactions is the sign of delta S positive? So this first reaction is the volcano from elementary school, where we have baking soda and vinegar become acetate and water and carbon dioxide. Delta S here is positive, which means that entropy is increasing because we're making a gas which has more entropy than an aqueous solution, and we're also making more independent particles. Two molecules, hydrogen carbonate and acetic acid, combine to form three different molecules. The second reaction, cadmium ion plus sulfide ion becomes solid cadmium sulfide. We've seen this reaction before when we talked about making yellow pigment, when we talked about solubility. Entropy for this will be negative. Entropy will go down because we've taken two independent particles and made them one thing, and we've taken aqueous solutions and made them a solid. The third reaction is sucrose and potassium chlorate become CO2 and water and potassium chloride. This is the exploding gummy bear reaction that you should check out on YouTube if you haven't already. And so in this case, we've got 9 independent particles on the reactant side becoming, 31 independent particles on the product side. So we have more independent particles. We also have more gases on the product side. So delta S for this will definitely be positive. Snow melting. Snow melting is another way of saying that we have solid water becoming liquid water. Okay, we said that liquids have more entropy than solids, so yes, delta S will be positive. And finally, we have oxygen becomes ozone. And here we actually see that delta S will be negative because we have 3 moles of gas becoming 2 moles of gas. So we'll talk more about this in the other screencast, but entropy can be thought of as being related to probability, the idea that a particular arrangement could happen. And so we can express that mathematically with Boltzmann's equation, and we introduce the idea of the Boltzmann constant. And that the key here is to think about all of the microstates or the ways that a system could be arranged. So it's more probable that the molecules would be arranged randomly in a container than that they would all be on one side. So you're never worried about being suffocated because all of the oxygen moves to one side of the room randomly. That's very improbable. Entropy tells us that the oxygen, the air, is going to spread out over the whole room. Okay, so be sure to check out the additional entropy and probability screencast to get a little bit more depth there.